So in the last class, we have discussed about the correlation matrices, which are useful for us to find the correlation in a LTI system and find the correlation between signals in a system, in a LTI system. So we discussed about how we can find the correlation matrices. The correlation matrices are in different manners. Could be autocorrelation matrix. Autocorrelation means you are finding the correlation between the same signal. So if you're finding the autocorrelation at the input of a system, so let's take this box as the impulse response of the system. So the transfer function of the system is given in this box. So once you know the input and the output, and sometimes you might know the transfer function also, then you can compute the autocorrelation matrices at the input, and that autocorrelation matrix is given in here. So autocorrelation matrix can be computed. So in here we have to keep in our mind that autocorrelation function, autocorrelation matrix is defined for m-dimensional vector. That means like it is for a finite dimension. For a finite dimensional random vector, it is defined. So the autocorrelation matrix will be a finite sized matrix. What I mean by finite size means like you can count the dimension. It is not uncountable. So you can count the number of elements in the matrix. So once you know the random vector that you are considering, then you can compute the autocorrelation matrix for that certain dimension. So why we are taking this finite dimensional vector is that normally we sample finite size samples for a unit time in a digital circuit or such kind of systems, for example. So normally we only take finite size samples, and we store those finite size samples in a memory space that is sufficient to store that samples. So because of the memory issues and all those resource constraints, we can only store up to a finite number of samples. So because of that, we are actually sampling the input signal and storing the input signal in the memory space. So that sampled finite samples can be represented as a vector, and that vector can be formed into autocorrelation matrix by considering the autocorrelation operation. So in the last class, we discussed about how we can form this autocorrelation matrix. This matrix is really important for us when we are, solving problems related to the LTI systems, and also solving problems related to filters, which we will discuss about in the next classes. So in those classes, we'll be discussing about Wiener filters, adaptive filters, those kind of filters. So when we are discussing about those filters, um, what we are going to check is this autocorrelation matrix. We are going to check whether this autocorrelation matrix. So we also going to discuss about other correlation matrices, and then we are going to use these matrices to identify, for example, the transfer function of an unknown system. Then these kind of correlation matrices will also be used to uh, find the gap between the input and the output. So such kind of applications are required in cases where we have differences between the input and the expected signal. So if you are receiving, as we discussed in previous cases, if you are receiving a signal over the phone communication, let's say when we are receiving a signal through our phone, it contains some noise. So if the if the system, let's say the system gets an input signal xt, and then you are having some noise in that signal, so you have to add a filter in between, and then you have to get the output. And then also you need to check whether the output is exactly something similar to the original message that was sent. So in order to check those things, we need to compare the similarity between the original signal and the received output signal. So such kind of similarities can be calculated using correlation matrices. So that is therefore an important metric that we'll be using to compute the similarity between two signals. So most of the time, once we remove the noise, we try to compute the similarity between the received signal and the expected signal. So we will, try to use these correlation metrics in the next sections. So for that, we have to keep in our mind how the autocorrelation matrices, then other correlation matrices are defined. So for a general case, the autocorrelation matrix can be defined like this, and it will uh, most of the time it will be a square matrix. It will be a square matrix because we are going to consider a certain m-dimensional vector, and we are going to compute the autocorrelation values by considering some uh, delays added to that, and then we are going to compute the autocorrelation function at different time indices. So the autocorrelation function, autocorrelation matrix will therefore be a square matrix, and it will be a symmetric matrix. And so most of the time in general, it will be a square matrix, and it will be a symmetric matrix. The diagonal will be same all along the diagonal. Around that, the elements will be symmetric. So these two elements are same. And this far end element is same to this leftover far end element. So because of those things, the autocorrelation matrix will be symmetric. The property will be that it will be symmetric. If we are considering a wide sense stationary process, or WSS process, the autocorrelation matrix will show some special properties. So the general matrix looks like this. The general matrix can have different values for this autocorrelation metric. So different values could be here, right? So, however, the WSS process, it's having some differences in terms of the values of autocorrelation that comes in here. So basically, we are computing autocorrelation values for each component, and those autocorrelation values will not depend on time. So if it is a WSS process, then the autocorrelation value will be a value which does not depend on specific time instances. It will be depending on some time gap between two time instances, T1 and T2. But it is a value which is constant because it is depending only on a time gap, not on the time instance, which could vary with the time. So values of these autocorrelation elements will be constant when the process that you are considering is a WSS process. And the metrics will also be symmetric, and it will be complex symmetric, we call that. The reason for using complex symmetric is that some of the signals in the random process can be complex, that they will have complex magnitudes. And if that is the case, then sometimes the autocorrelation function values also will be complex values. Then the output matrix will have complex values inside these elements. So the final outcome will be that it will be symmetric and it will be complex symmetric, which means that the complex numbers will also be symmetric along the diagonal. Such kind of matrices we call as Hermitian matrices. And therefore, for a WSS process, the matrix of that we obtain for the autocorrelation will be a Hermitian matrix. Then the matrix will also be positive semi-definite matrix. So what I mean by that is that once you calculate the eigenvalues of the matrix, the eigenvalues will be non-negative. The eigenvalues will be non-negative, which means that the eigenvalues can either be 0 or they can be above 0. So if you can calculate the eigenvalues of the matrix, and if you can find out that each of the eigenvalues are above 0, then you can say that this matrix is a I mean, if all the eigenvalues are above 0, then that is a special condition. And that condition is that the matrix is a positive definite matrix. If the of all the eigenvalues are above 0, and I mean, if the eigenvalues are not equal to 0, that means that for sure all these eigenvalues are all positive. So because of that, that kind of matrix is known as positive definite. If one of the eigenvalues are equal to 0, then we call the semi-definite matrix. That means one could be 0. One of the eigenvalues could be 0. So the most so for the WSS process, the requirement is that the matrix will be positive semi-definite. So the if you can find if you are given a certain matrix like this, and if you are asked whether this is a semi-definite matrix or positive definite matrix, you can find the eigenvalues. By checking the eigenvalues, you can say it is either positive semi-definite or positive definite. So for WSS process, most of the time the matrix will be positive semi-definite. So with that, I think we discussed about the autocorrelation matrices mainly, and we finished that part. After that, we discussed about the LTI systems, and we discussed about the importance of, like observing the system under frequency domain. So we can do observations in either time domain or in the frequency domain. However, like in this situation, when we are doing time domain analysis, we are able to observe the fact that these time domain systems involve convolution. Convolution is a costly operation, and that requires a lot of resources for the system to compute. So therefore, once we are using frequency domain, we can reduce the computational cost. So that is done by this relationship that the output of the system will be the multiplication between the transfer function and the input signal in frequency domain. If we turn all the signals of input signal and the impulse signal, or I mean the system response, if we turn that into frequency domain, we'll be able to get the multiplication of those two components, of those two signals, and then we can find out the final output. So the HF in here could be something like a filter. So if you have a certain input signal, you can add a filter to filter out the input signal's noise, let's say. So YF is the noise filtered signal. So in order to find this YF, we can find the frequency domain representation of the input signal XF, and then we can take the multiplication with the this filter, multiplication with this filter. So in the frequency domain, we can take the multiplication, and the multiplication will be done with the relevant frequency components. So after that is done, we will be left alone with some kind of a frequency domain signal, YF. So since frequency domain signals are not that important sometimes for us, again, we turn this into time domain signals. And then we can make some predictions about the system. So if we are filtering noise from that signal, then we can see from the output signal whether the noise has been filtered or not. So in order to see that, we need to turn this into time domain signal, and then we'll be able to see that noise has been removed from the input signal. So that kind of operations can be done. I discussed about the fact where we are going to use the correlation functions. So the correlation matrix is used widely in these LTI systems, where we are going to compute the similarity between the received output and the expected output. So this is one of such systems. So we have input signal Xn, and then we have a certain system called Hn, and then we have output Yn. Then we are going to compute the similarity between the output and the original Xn signal. And by doing so, we can find out the sort of the error between the input original signal and the received output signal. If the error is too much, then we can say that some kind of noise has been added to the output, some kind of fluctuations has been added to the signal, such that the original signal has been diminished in the signal. So by doing such kind of for calculating the differences between the Yn and the Xn, we need to use the cross correlation function. So the cross correlation function can be defined mathematically using these equations. And I think I discussed about several equations that we can use to define the autocorrelation function of a signal. So in that class, I think we discussed about the autocorrelation function of the white noise. White noise's autocorrelation function is given by n naught over 2 delta L. So the magnitude of the autocorrelation will be n naught over 2. Then I think these equations we have discussed about the time domain, relationships that the input signals correlation has with the output signals correlation. These models, as you can see, like convolution based signals. So in all these equations, we can see that convolution operation is used between the input and the output, and between the impulse response. So those kind of time domain signals are there. However, like if you want to get the work done in the frequency domain, we have to use the Fourier transform, or we have to use the Z transform. So the reason is, we have discussed also this, that the computation in the frequency domain is less complex when compared to the time domain. So rather than doing in time domain, we can do in frequency domain. And then finally, we can transfer it back to the time domain using inverse transform functions. So these are the kind of relationships that we discussed about, that showed the relationship between the input and output of a system in the frequency domain. So this YF represents the output of a system in frequency domain. Then PXY EJW represents the power spectral density of the power spectral density between the X and Y signals of the system, which is denoted as a function of e to the j omega. And we also derived, we also saw this definition, which represented this PYY, e to the j omega, which means that the power spectral density of the output signal is equal to the magnitude squared of the transfer function of the system into the power spectral density of the input signal. So this is important for us to define the relationship between the input-output power spectral densities and find the transfer function of the system. However, like in this case, what we can observe is that only the magnitude of the transfer function can be obtained, right? By taking the ratio between these power spectral densities at the output and at the input, we can get the magnitude of the transfer function only. But there could be a phase to the transfer function. So in order to do that, we have to sometimes go beyond the Fourier transform and use other transforms that can do that can give us that information. So, so in that class, we have discussed most of the time domain relationships that are given in here. So these are the time domain relationships between the correlation matrices, and these are actually some relationships that you can state about the input correlation and the correlation between X and Y signals. So these relationships are time domain ones. So sometimes like working with time domain is not that easy, because sometimes finding the output power and then the other parameters might be complex. So when we are working with the frequency domain calculations are much more simpler than convolution. So because of that, sometimes it's better if we can do the calculations in the frequency domain. So when we are doing the calculations, we have different options. One kind of option is the Fourier transform, and the other one is the Laplace transform. Another one is the Z transform. When we are discussing about the Fourier transform first, the Fourier transform has different types of doing the transform. So if we do the Fourier series transform, then we are doing it for specifically periodic signals. So for periodic signals, we can do Fourier series transformation. Then for aperiodic signals, or signals that do not show any kind of a periodical change, then we can apply the Fourier transform on the signal. So there could be different frequency components. Once we convert the time signal into frequency domain signal, there could be different frequency components in that signal. So we will be able to see that once we do the transform and obtain the plot of the output signal. So output signal will have fundamental frequency component and harmonic components. So fundamental frequency component is the main frequency that the original signal was generating. And sometimes other harmonic frequency components also might be created once the original signal was created. So sometimes we need to get these harmonics filtered out, and we only want to hear the fundamental frequency component. So so it's worthy to note that there are harmonic signal components and fundamental frequency components. So harmonics are multiples of the fundamental frequency value. So when we are doing Fourier transforms, this is like a overview of all the types of Fourier transforms that can be done. So we can divide the Fourier transforms into two types mainly: continuous time transform and the discrete time transform. So when we are doing the Fourier transforms, we have to consider the specific transform method. So if it is continuous time, we can have Fourier series and Fourier transform for the continuous time signal. And if it is discrete time based Fourier transforms can be considered to do the transform. So, I mean, discrete signals are more preferred in practical applications in the real world, mainly because, as I said, we have only finite space, memory space in our circuits and in our, in our designs. We don't have infinite memory space to store all the samples of the signal that we are giving to the system, or we are that we are sampling. We don't have enough space, so we have to have only finite number of samples. So depending on the available memory space, we will be sampling them and we will be storing them in the memory space. So in most real world applications, we will be using these discrete time signals, and we will be working with this discrete time Fourier transforms. There are Fourier transforms in either Fourier series format and in the Fourier transform form. So when we are discussing about these main ones, they are actually defined for infinite time duration. However, like discrete Fourier transform is the transform method that is defined for finite size signals. So as I said before, real-time signals or real-world signals are finite size signals that we are going to actually process inside a circuit. Although there are infinite number of signals in the signal, we only can, like store only a finite size signals at a certain time instance. So when we try to do the transform, we have to use discrete Fourier transform uh, in such kind of cases where the number of samples are finite sized. So in that discrete Fourier transform, they are actually assuming that the signal is a periodic signal, and then based on that assumption, they are computing the Fourier transform. So then, and so in most of the numerical calculations, we are going to use fast Fourier transform to compute the Fourier transform um, without using a lot of resources. So a simple way of doing the Fourier transform in the discrete domain is the fast Fourier transform method. So in MATLAB and all, we have this FFT, command to calculate the fast Fourier transform of a certain discrete signal. So fast Fourier transform is a simplified way of DFT method or a discrete Fourier transform method. So the definition of Fourier transform is given as the the main concept of Fourier transform is that any time domain signal can be represented as a combination of sinusoids. So any time domain signal that we have, we can denote by combination of sinusoid signals. So using that concepts, we can define a certain time domain signal in the frequency domain using frequency domain sinusoids. So that was the theory behind Fourier transform. So I think we will discuss about those Fourier transform in today's class. So we'll be discussing about mainly about these components today. Most of the time we will be doing this theory, Fourier transform. We also will be discussing about the main concepts and also the limitations of Fourier transform. So all the Fourier transform has its benefits when looking at the frequency domain representation of a time domain signal, we are still unable to get some things done using Fourier transform. So because of that, sometimes we have to use other transform methods to maybe improve the performance that we expect from a system. So another type of transform that is used is set transform. Set transform. So set transform is used instead of Fourier transform for some simplicity in calculations. Then we will will be discussing some etc.
Madam, excuse me, we can't hear you, madam.
Hello, can you hear me now? I think.
Yeah, now it's okay, madam.
Great. So I think got interrupted with a phone call. So normally that happens. So I think I will be discussing the rest of this. So Babler transform also we will be discussing. And then we will discuss about, doing some simulations related to those concepts. Right. So this is what we are going to be discussing. So about the Fourier transforms, Fourier transform we will be discussing a little bit, but most of the time I think we will discuss about the Z transform, which would be a convenient form to deal with when we want to turn a signal into the Fourier or a frequency domain. So Z transform is simple, and we can, I mean, consider this for kind of when we can consider it's a transform for identifying more features of the signal, more than Fourier transform. We will discuss about that. So the Fourier transform, I think we discussed in the last class the overview of that. So basically, I think we have discuss most of the things, but I think we didn't discuss about the Laplace transform and the Z transform. So for doing that, I think I will just give us some explanation about the Fourier transform for the start, and then we will discuss about the Laplace transform and the Z transforms. So Fourier transform, as I discussed about, so it is defined for finding the frequency information of a signal, frequency information of a signal, and find out the frequency components of that signal and the magnitudes of the frequency components. So the limitation is that the although we find those frequency components, the Fourier transform does not exactly tell when in time the frequencies exist. So the problem with the Fourier transform is that although we have this, frequency components and their magnitudes of certain frequency components. So the magnitude of the frequency component is given in the y-axis. So you have a certain signal, and if you have a certain time domain signal, the maybe if you have a sinusoidal signal, then the Fourier transform version of that will have some fundamental frequency component and maybe some like multiples of the fundamental frequency component. So those kind of ones will be there as the output of the Fourier transform. So in here, the magnitude of these frequency components are given. However, like we don't know exactly at what time this frequency component is occurring. We don't know that. So in order for us to, get that, we have to use other transforms to find out the exact time at which this frequency component exists in the signal. So the Fourier transform does not exactly tell us uh, where the time instance of the frequencies occurring. So therefore, frequency domain, the Fourier transform is ideal for situations where we have stationary um, signals, so signals where the properties do not change. So Fourier transform is suitable for um, situations where we have stationary signals. So the meaning of stationary signals is that like, if we have a signal like this, we have a sinusoidal signal uh, that we receive. If the received signal is not changing its properties over time, then that signal will be considered as a stationary signal. For a stationary signal, we can uh, get the Fourier domain representation, and then we can make some predictions regarding the stationary signal. So that is the reason that we always discussed about the wide sense stationary processes and strict sense stationary processes. When we discussed in the last sections and last lessons, we focused a lot about this WSS process. So most of the time, this WSS process, which is a stationary process, um, can be analyzed using Fourier transform. So WSS process is a stationary process, which means that its properties do not change with the time. So the properties are kind of constant over time. So the Fourier transform can be used to study its properties. So for WSS processes, Fourier transform can be used. However, in the real world, the actual processes might not be stationary all the time. There could be some non-stationary aspects to this signals. The signals can abruptly change in some points. So sometimes some abrupt changes in the magnitude can occur due to some noise or some kind of interference. And in that case, the magnitude of the signal will change, and sometimes some frequencies might change in the signal. So some higher frequencies could be added to the signal, and the signal will distort in a certain manner. So in such kind of cases, some additional frequencies might be added to the signal. So those kind of sections cannot be identified using Fourier transform. We have to use some special transform methods to identify those. So the special type of transform that can be used to identify those ones will be wavelet transform. And that wavelet transform is like a technique that uses like a part of a signal with a high frequency to compare with these signal components. So you will be basically using correlation again. So correlation is an important matrix. Therefore, correlation will be again used in here to compare the wavelet transform, this section of wavelet transform with the original signal. So if they are similar, then we know that the frequency that has been added in this part of the signal is some kind of specific frequency that is of the wavelet. So this wavelet concept we will discuss further as well, which is an important concept that helps us identify different sections of the signal and separately identify their frequency components. So such kind of wavelet transforms are required in situations where we have signals that are changing abruptly, changing very quickly, suddenly. Okay, if a certain signal is suddenly changing at some time instance, then we have a non-stationary signal. So in that case, we might need wavelet transform to observe those abrupt or sudden changes in the signal. So wavelet transform can be used therefore for applications such as uh, I mean uh, such as signals, for analyzing signals that are abruptly changing, which can occur in applications such as earthquakes, sudden changes in the environment, and sudden noise addition to the received signal. So such kind of cases, wavelet can be used. So wavelet transform is something that we can do using MATLAB. So we will do some MATLAB simulations also in the upcoming classes. But I think today I will not be doing the wavelet transform, but it is one of the things we are going to discuss in the upcoming classes. So this will be used, wavelet transform will be used to identify different features of the signal. Right? So it can be used for feature engineering, right? Feature engineering, and feature engineering is a engineering where you are going to detect features in the data signals. So you can use this wavelet transform to identify features in a signal. So we can use some MATLAB and other tools that are available even in other platforms to do this wavelet transform and identify different parts of the signal. So that is regarding like the limitations of Fourier transform, right? Limitations of Fourier transform. So like um, uh, like uh, so these kind of non-stationary signals happen in situations where you have sudden changes in the signal. In cases where you don't have such kind of sudden changes, and let's say we do get a signal which is stationary over time, we will be using Fourier transform. So the Fourier transform is useful for stationary signal analysis, and the stationary signal analysis will be also useful in situations where the conditions of the environment is not changing rapidly, right? The system does not change very rapidly. So in this module, we'll be basically looking at LTI systems, as I said. So linear time invariant systems, right? Linear time invariant systems. So in those systems, under stationary signals, we will be using Fourier transform and Z transform to observe the signals in the frequency domain. Right. So we will be discussing about the input output of a signal. So the signal will be given as input to a certain LTI system with a certain impulse response Hn, and we will obtain output Yn. So we will consider first for scenarios where this input signal will be a stationary signal. For such kind of cases, we will be discussing about Fourier transform and then about the Z transform, as I said. So I think we discussed about the definition of Fourier transform in the last class. So that definition is given by mathematical equations and mathematical definitions. So the definition of the Fourier transform can be given as that any time domain signal can be represented as a sum of multiple sinusoids. So this can be denoted using this equation gt equals minus infinity to plus infinity, where the frequency domain signal gf is denoted using e to the 2 pi ft df, 2 pi ft functions. So in terms of exponential functions, which will create sinusoids, we can denote the time domain signal. So this actually gives us summation of sinusoids. So the time domain signal will be a summation of sinusoids. So any time signal can be denoted using a summation of sinusoids. So that is the definition of Fourier transform. If we take the inverse Fourier transform, the inverse Fourier transform means that so this is the Fourier transform concept. So if you have a Fourier domain signal, you can convert into time domain signal. So this is actually the inverse Fourier transform operation. So if you are converting time domain signal into frequency domain, you can use this equation to convert that. So the equation is that you convert the time domain signal into frequency domain. In there, we have to take the e to the minus j2 pi ft over dt. Then you will get the frequency domain representation of the time domain signal. So this is the frequency domain signal. So this is the transformation from time domain to frequency. So this is the Fourier transform. This would be the inverse Fourier transform. So these are the two equations that govern the Fourier transform. So as I said before, there are other transform methods also that are used, which are, I think I will give a brief explanation, which are basically Laplace transform and Z transform. So we discussed about transforms mainly in the last class. So giving like a briefing about that, we discussed about Fourier continuous time transforms, continuous time transforms, discrete time transforms. Then continuous time transform, we discussed that under the Fourier domain transform, Fourier transform. Then we can do that also under Laplace transforms. The discrete time one we can do using the Fourier transform and also is a transform. If we have a continuous signal, we can compute the Fourier transform. For the continuous signal, we can compute the Fourier transform. And if it is a periodic signal, we do the like Fourier series transformation. And then if it is a aperiodic signal, then we will convert the aperiodic signal into Fourier domain using Fourier transform, like mathematical definition. So we have Fourier series and Fourier transform that we can apply on the continuous signal, right? So this is something we discussed in the last class. So with regard to Laplace transform is also used for the continuous time domain signal transformation. The only difference with regard to the Fourier will be that in here you will be um, representing the uh, time domain signal using a parameter S, which is defined using real and imaginary components. So the S is the domain that you are going to be. It's like it is the variable of Laplace, and the S variable is denoted using sigma plus j omega, and sigma is the real component of S, and omega is the j omega is the complex part of the uh, S variable. So the S variable consists of both real and imaginary parts, whereas in Fourier we are denoting all the functions. The output of the Fourier transform will be in terms of j omega. The output will be in j omega terms. But in here in the Laplace transform, the output will be in terms of S. So the output will be in terms of S, and the output will be that S will be consisting of real component and the imaginary component. So this is the imaginary component. J omega is the imaginary component. So once you do the Laplace transform of uh, a time domain signal, let's say time domain signal is gt, the Laplace transform of that signal can be given as gs. In generally, you can give it as gs. So the Laplace transform you can denote using a L. So the output will be gs. So for a LTI system that we are considering, we have a certain input xt in the time domain. We can convert that into S domain, and then we can write it in the Laplace format xs, and then output will be yt. The impulse response will be ht. So the Laplace transformation will give hs for the impulse response and ys for the output signal. The relationship between these will be like this: ys hs into xs. So the multiplication will be applied there also. So therefore the computation will be using multiplication, which is less complex than convolution. So this kind of a relationship can be used when we are studying LTI systems using Laplace operations. However, the Laplace operation is done for the continuous time. So the continuous time is useful for cases where we are obtaining samples of the signal for continuous time instances, right? So in normal real world scenarios, we are not going to have all the data values of all the continuous time instances, right? We have to only we are only able to sample like up to a certain frequency that is possible. Intermediate positions between these two frequency components cannot all be captured, right? We cannot capture all the data simples between the two signal points because of the limitations of our systems, right? So our clock frequency is determining how we can sample the signals. The clock frequency of the system that is obtaining this data is not high, then samples will be less. There will be less number of samples. So because of that, the continuous nature of the signal will be lost. But that is the level that we can achieve. So continuous time domain signaling and sampling might not be really practical in situations where actually practically implementing these systems. In such kind of cases, we have to analyze the system under discrete time domain. However, like if you're doing theoretical calculations, and you're going to develop some kind of a mathematical model, some kind of I mean some new idea regarding the signal processing and something related to that, then we can do that in the continuous time domain using mathematical models, some assumptions. Okay, so you have to make those assumptions such that the theory that you're presenting will be very close to the real world truth. So when we are doing anyway, like the actual implementations, you will be actually only like sampling only finite places of the signal. So finite signal samples are only available in this kind of situation. So in such kind of cases, you will be using Fourier transform and you will be using Z transform. So focusing on the Z transform. Z transform is defined using mathematical models given by this this equation. So if you have a certain signal xn, its Z transform will be denoted using xz. So since this is discrete, we will be taking the summation, not the integration, and we will be writing that the time domain signals uh, will be considered, and it's set to the minus n will be considered. So this is the, like I said, transform definition in mathematical format, right? So using this, you can convert you can convert the time signal into Z domain signal, right? So all the time you can convert time domain signal into Z domain, and there are some specific equations that are available to do that transformation. So up to this point, any questions? Okay, so this is a mathematical equation, and I mean, in this module, if there's some kind of a like mathematical equation that you need to remember, I will let you know, right? So anyway, like this is something that you might need to keep in mind. You might need to remember this equation, which is a simple equation which denotes the transformation, and you just need to multiply the time domain signal with the Z to the minus n. So in here, you are taking Z to the minus n, and you are taking the summation over all the time indexes. So this is how the transformation is done. However, like I said, transformation is basically, I mean, used in multiple places in the real world. So it is used to observe the oscillations or any kind of exponential behavior of output signals or the signals that we are observing. there are any kind of oscillations or exponential behaviors of the signals, we can easily identify using the Z transform. So that is regarding Z transform as importance, right? So Z transform can be used for like sudden changes like oscillations and exponentials in the signals. So this is like not very sudden, but like you can see some kind of a signal magnitude change over time. So the exponential behavior means that signals amplitude might change in an exponential manner. The frequency behavior also can change in exponential manner. So such kind of things can be observed using Z transform. The frequency response of the system, if it is changing over exponential term, then you can observe that using Z transform. Also, you can observe the convergence of the frequency components using Z transform. So let's say if the frequency components of a system converge to a certain frequency value, that also you can find using Z transform, whether the convergence happened or not. So I'm not going to go into details regarding the Z transform and its definition, but we are going to use that Z transform to find some important statistics of LTI systems, right? So as we discussed about, so our main concern is to like study LTI systems. So LTI systems are required for us mainly because we are going to do like processes such as removing noise from received signal, right? Removing noise from the received signal. So this is important in practical applications where we are receiving a noisy signal through the phone, right? Through the phone or through our microphones or some kind of recordings that we are taking about the environment. If you are placing some sensor, then the sensor might take some readings, but those readings might have some noise. So whenever you have some noise, you have to denoise that signal. In order to understand like which frequency components need to be removed, you need to consider Fourier transform or Z transform, then like calculate the necessary filters, I mean necessary frequency components that need to be removed. And then after you identify that, you can identify which filter is required to do that frequency cancellation. Okay, so we are in that process. We are in that process of designing systems that can remove noise from the input signals and then improve the quality of the signal. Okay, I hope it is kind of okay for you to understand by now. So the main idea is for us to design a system, and design filters that can give us very high quality signals. So if we consider a system, let's say this impulse response is this. So output is yn and input is xn. Then we can consider the Fourier domain of this, right? So Fourier domain analysis we can do. So one relationship will be the input will be xf in the frequency domain, output will be the yf, right? In the frequency domain. The transfer function will be hf. We can then find the relationship of this operation using yf, hf into xf. And then we discussed earlier about the power spectral density. Power spectral density can be also used to define the relationship between input and output. So the power spectral density, if we are denoting using letter S, it will be SY. Then you can get the frequency and like power spectral density is varying with the frequency component. So then the HF and its magnitude can be taken into consideration, and then the input signals power spectral density can be taken into consideration. With these two relationships, we can build the relationship between the input and the output. So when we are dealing with these kind of systems, uh, as I said, Fourier transform can only find the magnitude of this transfer function. If you want to find the transfer function, Fourier transform might not be able to find the phase response of this. So magnitude only we can find, but phase response we cannot find. So therefore, uh, that is one of the limitations of the Fourier transform. And also another limitation of the Fourier transform is that when we are doing calculations, I mean, for easiness, we are using is a transform because Fourier transform uses and is based on the e to the j omega components. And in order to like work with all the calculations, it's kind of challenging when we are using Fourier transform. So DTFT or discrete time Fourier transforms is not convenient for the like system analysis because it contains a lot of e to the j omega components to work with, e to the j omega components to work with. So instead, we are going to use Z transform, which is a more convenient method. So Z transforms are defined uh, in certain manners, and there are Z transform tables. So using those tables, you can find the Z transform of that certain parameter or a certain signal. So when we are working with the LTI systems, what we are very interested is about the autocorrelation and the cross correlation of signals, right? So when we have such kind of system, what we want to do is that we want to find out the like autocorrelation at the input and the autocorrelation at the output, those kind of things. So in order for us to find those, we need to compute the autocorrelation value in terms of uh, the Z domain, and then we can convert that into time domain. Right? So finding the time domain function is difficult. So because of that, we are first going to use the Z transform, and then we are going to take the inverse Z transform. Once we find the autocorrelation value, then we can then take the inverse of the Z transform and find the time domain signal. So we will do that using some example. Right? So any questions up to this point? Okay, another thing I would like to mention here is that the main equation that can be used to find the correlation at the output is that um, we can denote the correlation of the output using RYYZ, right? RYYZ to denote the autocorrelation at the output, right? RYYZ to denote the autocorrelation at the output. And it's equal to the HZ multiplied with the HZ inverse with the multiplied with the RXX Z. So this is the output input autocorrelation. So with this equation, you can build the relationship between autocorrelation values at the output and the input. Most of the time, we will be able to find the autocorrelation value at the input if we are given the input signal. So what we need to find is this, output autocorrelation function. So so let's consider one example and then we will try to find the autocorrelation of the output. Right. So in such kind of examples, we need to first find the autocorrelation value. The autocorrelation value RYY using the available data regarding the HZ and the RXXZ. So we will consider this example. So I want you also to solve this problem that I'm mentioning here. Okay. So as an example, I will consider this scenario where we have a certain random process. Consider a random process with zero mean and with autocorrelation at the input given by Rx. So this is simple Rx n denotes the time index and sigma squared delta n. This is the input autocorrelation function. Let's say there's a input autocorrelation function. So that one is given. And then we are also given that the process is filtered. The process is filtered using a filter HZ, right? The process is filtered using HZ. So HZ is the process used to filter or the transfer function of the filter. HZ is given. So HZ is equal to 1 minus lambda and then 1 minus lambda lambda Z inverse or Z to the minus 1. Right, so this is 1 minus lambda divided by 1 minus lambda Z minus 1. So we are asked to find the autocorrelation value at the output. So what is the autocorrelation value at the output? For n equals 2 to n equals from n equals 2 to minus, sorry, n equals minus 2 to n equals 2. So in this time indexes, what is the autocorrelation values at the output? So that you need to find. So you need to find the autocorrelation at the output. So this time domain value you need to find, right? So this time domain value you need to find. So H is given using Z domain. And then there's a hint also that is given. A hint is also given saying that if there's a uh, Z domain function, which is 1 over 1 minus a z inverse plus a z divided by 1 minus a z, then that expression can be uh, denoted in time domain using this xn equals a to the n, absolute value of n. So with this information, you're asked to find like the uh, output autocorrelation value. So this is what you're asked to find. So you're given this as the hint. So now what we need to do is what we need to figure out. So in solving this equation and in this problem, you need to go step by step. You need to consider the relationship between the input and output autocorrelation functions. And then you have to consider that in the Z domain. Then you can try to find the autocorrelation value in Z domain and then find the time domain representation of the output. So first thing is that you can find the Z domain representation of all the signals that you know, right? Z transform of all the Z transform of the input signal you can find. So consider that the Z transform applied on a delta signal is 1, right? When you apply Z transform or Z transform on a delta signal, the output is 1. So this is the hint. Second part will be considering the relationship of autocorrelation, finding the autocorrelation at the output in Z domain, right? So finding the autocorrelation of the output in the Z domain, and then finding the time domain representation of the output autocorrelation value. So these are the things that you need to do. So will you be able to try out a little bit on your own? So this is the question. So I think you can take a maybe a screenshot of this, sum. I will go down and I will explain how we can solve this sum. So these kind of sums are the things that we have to solve, and they are actually useful for finding, as I said, some like autocorrelation, cross correlation functions. So these functions are again required for us to like find the noise existence of a signal, and so on. So these kind of metrics need to be found in the system. So we can do that using softwares. Sometimes like we need to know how it happens um, using the mathematical models as well. So that is what we are trying to do here. So first and foremost, we have to find the Z transform of the input signal. So the input signal has been given. So we have been given the input signals autocorrelation function in the question. So we have to use that as the first step. So first we need to consider the Z transform of the input signals autocorrelation value. So we have been given this one. So if you have any questions related to how I'm solving this, please let me know. So the autocorrelation function at the input is given by this sigma squared into delta n. So when we take the Z transform on both sides, the delta n function will be equal to 1 when you're doing Z transform. So the uh, output Z transform will be looking like this, where Rx Z denotes the Z transform of the X signal, and sigma squared, it will be equal to sigma squared because delta n's transformation will be 1. So the sigma squared is a constant value. So this is a constant value, so you can take it out. Then second thing is finding the RYZ. RYZ is denoting the output autocorrelation value in terms of Z domain. This one we can denote using this relationship that I mentioned to you, which is Hz into H minus 1 into the Rxz. This relationship I think I mentioned in the earlier sections. So this is something important relationship that you need. So this is the relationship that I mentioned about the output autocorrelation and the input autocorrelation functions. So you can denote it like this. I will put two y's to denote autocorrelation, but it's not it's fine if you use just ry as well. Then you are trying to find this one. So you need to find the rest of this expression. So Hz is given by the 1 minus lambda over 1 minus lambda z inverse. This one you can multiply with the Rxx no, you need to multiply this with the inverse of Hz, which is 1 minus lambda divided by 1 minus lambda z. So when you're once you're taking once you're substituting z minus 1 to here, what happens is that the z inverse which was already there will be multiplied with 1 over z. So in here the term will be lambda z. So if you can't understand that, I will repeat that. So in here, the HZ is given by this. HZ inverse is given by this, where you are substituting Z with Z inverse, or Z into minus 1 in all the places where Z occurs in here in the HZ. So wherever there is Z inverse, you are going to substitute, sorry, wherever there is Z, you are going to substitute Z inverse. So in here, when you're having this, it is like lambda over Z, right? So this will be converted to lambda over 1 over Z. Once we are substituting Z inverse instead of Z. So with that, this small part will be equal to lambda Z. This part will be equal to minus lambda Z. So that is why it came in here like this. So then you can multiply that with this sigma squared. And that is how you will be left with at the end of the calculation of the, expressions. So you need to solve this further into a point where you can take the inverse. So we have been given a hint in this sum. We have been given a hint where the hint is x z equals 1 over this expression is equal to the time domain expression of a to the n. So anyway, we need to find some kind of a function like this in our calculation, so that we can turn it directly into the time domain version. So currently we are in the Z domain, and if we are having this kind of expression in our question in some section, we'll be able to substitute it with this a to the n. So in order to do that, you need to simplify this further. So as you can see, when you are multiplying this, you will be getting a fraction where the numerator and the denominator can be represented using, um, like a function which is having, Z terms and like Z minus 1 terms, like Z to the power minus 1 terms. So you need to decompose this fraction into partial fractions. You have to use partial fractions to decompose this. Partial fractions should be used, right? So have you learned about partial fractions in your mathematics? Anyone? So this is basically purely something mathematical, right? So when we are doing partial functions, you have to divide this expression into two functions, two separate fractions. So this one, first of all, we will first denote this as like this 1 minus delta, sorry, 1 minus lambda squared, and then 1 minus lambda z minus 1 into 1 minus lambda z. And then we can multiply this with sigma square. We need to get this into a format where we have two fractions, and we have been given a hint. That hint is like z x z equals 1 minus 1 minus a z inverse plus a z 1 minus a z. So once you have all this hint, you need to know that you need to have this kind of expression uh, in your calculations. And since we are trying to find two fractions in here, we can say we can assume that we need to form these kind of partial fractions in our output. So the partial fractions, there will be constitute of two denominators. Two factors are here. So we have to have two denominators. One denominator is 1 minus lambda Z inverse. Another denominator is 1 minus lambda Z. Right? So we need to find the constants that go in here. Could be some kind of constants, and we need to find that. After that, we can multiply. No, we have to get these two partial fractions. Then we can take the inverse of that. So before going to do that, I think we can consider this expression separately, and then we can find the um, equivalent expression of this term. So first we are going to, like, we can just, for the moment, we can just erase this one. We can try to find the partial fractions first. So 1 minus lambda squared, a sigma squared divided by y 1 minus lambda Z inverse, and then 1 minus lambda Z. So this can be equaled into two fractions. That fractions can be, those fractions can be denoted using two fractions which are having denominators of 1 minus lambda Z to the minus 1, then plus bz. So in here, actually, we have to consider the format that was given to us as the hint also. So because of that, we are going to take the numerator as bz and then take the new denominator as 1 minus lambda z. Then we can consider only the numerator on both sides. Consider the numerator on both sides. So when we consider that, we can write the numerator on both sides. So when we are multiplying it, it will be like this: bz 1 minus lambda z minus 1. Then we can compute the similarity. We can consider the similarities between these two. First, we can consider the z terms. By considering the z terms, we can say that there's no z term on this side of the function. There's no z term, so it will be equal to a minus lambda a minus lambda a plus b as the z terms, right? So these are the terms that produce the z terms. And then those things will be equal. So with that, we can say b equals lambda a. That is one equation. Then we can consider constant terms. Constant terms. Then we can write the constant in here. This 1 minus lambda squared, sigma squared is also constant. So that one we can equate to the constants on the right side, which is a. We can say a on this side, on the right side, and plus b. In here, there's a constant generating once we are multiplying bz with lambda z's inverse, or lambda z to the power minus 1. So the z minus 1 will be cancelled by z, and constant will be generated, which is b lambda minus b lambda. So with that, you will be able to have the constants. So that is how the constants are defined. And then you can substitute B with the lambda in here. From the first equation, you can get A minus B you can replace with lambda A, and you can say lambda squared A. Then in here you have 1 minus lambda squared uh, yeah, 1 minus lambda squared, and you can take it like this. Did you follow me, or is there any mistake in my calculations?
How did you cancel off the sigma squared?
Sigma squared cancel out. Where?
In the second step, from the second step, sigma squared.
No,
And
it's not cancelled. I did
Oh,
not
I'm
cancel it.
sorry.
It's just there, but I was just wondering something else. Is there any mistake in my calculations? If you see some mistake, just let me know.
Sigma squared, lambda squared. Oh, no, I wouldn't say. Could you explain how did you get 0 equals lambda a plus b, please?
In here, I consider the Z terms, terms that are containing Z on both sides. And in here, we don't have any Z components in the top, in the numerator, in the left side. On the other side, in this right side, you have minus lambda A and B as the Z terms.
Oh, so you took off these terms. Okay, I think that's the mathematical way of doing it.
You can do it in several manners. This is how I am doing normally, and I think you can do it in your, I mean, in different ways. I think this can be done in different ways. So
No. If you think it's the way, it's the way.
so if you are okay up to this point, we will go. I mean, I'm asking from the entire all the students. So if you have any questions up to this point, or if you see any questions in this point, you can let me know. So after you find the A, you can find the B. So you have to find the two constants, A and B. Then using those constants, you can define the final partial fractions of this expression in here. So in here, the problem currently is that with the A value that I'm getting, it's not easy for me to simplify this expression further. So I would like you to try to, follow it, calculate it on your own a little bit, and let me know whether you get a different answer for the A and B constants than me.
Are these the type of questions that we'll be getting in the exam?
I mean, I don't know exactly, but
No. In ballpark answer.
I think I cannot really understand what you're asking.
The type of questions, in the sense, context. Let's say in a question there are 3 or 4 parts. One part would be kind of something like this, and followed by the same context of questions for one question.
I can't understand what you're asking. I'm sorry.
How could I put it? So this kind of questions, will they be not the same one, but something different? let's say we have to answer 6 questions, and this will be these kind of questions will be a part of one of those six questions. Is it like that, or this will be a single question itself?
I mean, I haven't really decided anything, so you will get to know in the maybe next classes.
No, not this example. I'm saying the width of the question.
Yeah, I also need to decide that based on the time actually. So if the time is like, I mean, based on my timing, I will decide like whether it's a kind of a question or sub question, something like that.
Okay, I understand. Thank you.
So as of now, we will get the A as 1 minus lambda squared sigma squared over 1 minus lambda squared. So we will get something like this. Then we will get the B. Once we have A, we can multiply this with the 1 minus lambda squared or 1 minus lambda squared and sigma squared. So with these two, we will be able to get the partial fractions that we initially defined in here. So in here, we will be writing this expression in here. So we will be able to get the part 1 minus lambda squared over 1 minus lambda squared part as a constant, because they are in both A and B terms. So what we will be having is basically 1 minus lambda squared divided by 1 minus lambda squared within brackets. Then you will have 1 over 1 minus lambda z to the minus 1 plus lambda over 1 minus lambda z. This type of expression we will get. So I hope it is okay for you up to this point. If you get this, then you can see that this is similar to the hint that was given that said that you can convert that this is the type of expression that I have given earlier. So this expression is similar to what we have. So these two expressions are similar. So with that, we can say, okay, we can use the transform that we have been given. So this part is almost similar to this one. So in here, I have forgotten the z, which I need to put in here. So in here, there's a z also. So 1 over 1 minus lambda z inverse and plus lambda z over 1 over lambda z is something that we are having in here. So in that case, we'll be able to use the hint that was given and transform this part into the form where we can denote the expression in the time domain. So in order to get to that point, so we first need to get to the point we are finalizing the RY set. RY set, I think we finalized. So this is the RY set, final version of RY set. So this one is RY set. So this is the answer to the second one, second point. And then you will have the third point where you will have to take the inverse Fourier transform or inverse Z transform of the RYZ. And using the hint, we can say that the entire term that was given in the RYZ, apart from the constant at the front, will equal to the lambda into the n, actually, because this is in the time domain that we are going to take the inverse of. So I'm going to write the Z transform function again. It would be like this. So 1 minus lambda squared over 1 minus single lambda squared and into sigma squared. This we can write 1 minus lambda Z inverse plus lambda Z over 1 minus lambda Z. This one you can turn it to time domain. So time domain expression will be R y n one minus lambda squared over 1 minus lambda squared into sigma squared. This part can be substituted with lambda and n. So this is the time domain representation of the autocorrelation function. So this would be the requested parameter. So then another thing that was asked was the autocorrelation values for different time indexes. Since we are considering discrete time indexes, you will need to consider only a discrete time instances, and for that you need to calculate the autocorrelation value. So n equals -2, n equals -1, n equals 0, n equals 1, and n equals 2. And those values can be considered, and you can find the RYYN for those n values. When we are calculating them, lambda will be there as a variable or parameter in the output. So sigma and lambda will be there as the parameters in the output. So that will be okay, lambda and sigma squared. If we know those values, you can substitute. Otherwise, you can leave it as that. So with that, I think that question will be done like that, in that manner. So if you have any questions, you can let me know. So any questions in this part? If you have any questions, let me know. So in the meantime, I will try to give like 2 assignments during this weekend and upload to the LMS. So you will be able to have time to complete them. So I will give a deadline within 1 month time. So by that time, I hope that you will be able to complete it. I might not be able to, I think, give more time, maybe 1 month. I think I can give you to complete those assignments. So those assignments and instruction sheets will be uploaded in the LMS. I haven't still uploaded them. So once they uploaded, you need to go through the instructions. If you have any questions regarding the instructions, you can email me, and I will try to respond to that. So with this part, I will move on. I need to discuss about the FIR filters and IIR filters. So with the FIR filters and IIR filters, what we try to do is that we are trying to reduce unwanted signal components in our original signal. So if we are trying to if we are trying to consider a scenario, if we consider a certain scenario where we have a signal which has been distorted by some high frequency components, let's say, we want to remove those high frequency components from our signal. So if we have a signal like this, let's say this is like vertical, right? Not exactly what I'm showing, but all these points are sample points that we are sampling of a certain signal. So once we have these sample points, we can see that this signal is a certain distorted signal due to some noise that was included in the signal. So in that case, we need to observe the frequency components of that signal. So we are going to use either any kind of Fourier transform. So when we are using discrete time samples, we can use fast Fourier transform, discrete Fourier transforms to convert to the Fourier transform. So since fast Fourier transform is less complex and it has there are many tools for available for us to use, we can use directly FFT transform to convert this into the Fourier domain. So in the last class, we used FFT in the MATLAB to convert, I think, delta function and the sinusoidal function into the Fourier transform. So FFT can be operated on this signal. So once we do that, we will be able to see a spectrum of frequencies or range of frequencies of this signal. So that range of frequencies can be of a certain shape or certain might show some behavior. So let's say the signal looks like this. So it can have some different frequencies, and then maybe uh, like the frequency components might be reduced in some areas. So once we have this frequency spectrum, the frequency spectrum can be, um, you know, can be used to find out the regions of frequencies that we want and remove the unwanted frequency components. So for removing the unwanted frequency components, we have to apply a filter on this signal. So we have to apply a filter on this signal, and we have to design the filter components or filter coefficients appropriately in a suitable manner, such that only the frequency components that we require are getting filtered out. So we can consider this as a low pass filter, and this low pass filter is designed to remove the high frequency components that are included in the original signal. So I mentioned earlier about high frequency signal components included in the signals, right? So in that case, like sometimes we want to remove those high frequency components to get a more smoother signal in the output. So the low pass filter can be designed, and the coefficients of the low pass filter can be designed. Once you know the coefficients, then you can implement the system using the general, uh, architecture of the filter. So we will design the filter coefficients, and then using the filter coefficients, you can apply the you can create the filter. Then once you know the filter coefficients and once you know the function of the filter, you can multiply the original signal with the filter function, or you can multiply the filter in the frequency domain with the input signal or the original signal's frequency domain value. So these things can be multiplied and you can find the filtered signal as the output. So the filtered signal will look like this. The filter signal will have frequency components in this region. In the region that we try to filter out. So minus W to plus W, there will be frequency components. So the frequency versus amplitude we are plotting in here. So the plot will be of frequency and the magnitude of the frequency components. Let's say the origin lies here, let's say, just for the moment. So we can tell that the magnitude of the frequencies will be denoted in the y-axis. So this is the output of the output in the Fourier domain. So if you have the you need to take the inverse Fourier transform to find the time domain signal. So you can use inverse Fourier transform. In here we are using inverse fast Fourier transform, and we can like recreate the original signal, and you can see some difference in the original signal once you have filtered it. So it could be a more smoother signal as we have removed the high frequency components of from the signal. So it could be a more smoother signal than the original signal. So we can obtain smoother signals using the filters, and the filters can be designed such that the expected frequency components can be removed out. So the filters can be designed either in FIR format or in the IIR format, basically. And the difference is that in FIR filters, you have finite number of coefficients. Finite number of coefficients. I mean, the output actually more than this, the filters property is that the output of the filters response, or the filter response will be for a finite duration. So the filter response that we get will be for valid or available only for a finite duration. Whereas the IIR filters filter response will be shown as an infinite duration response. That means that the output of the filter response will be available for an infinite time duration. So we will see that basically using the mathematical models how that happens. I mean, basically how the infinite time duration is occurring for the IIR filters. So in the so it is something like like some infinite output means like it's something that is kind of out of our understanding how infinite outputs can be maybe generated. However, like using the I mean, based on the way this filter is created, infinite outputs are created from this filter. So the mathematical equations behind these filters we need to discuss, and also the block diagrams that define the functions or define how this filter is formed, we need to discuss. So when we take the FIR filter first, I will just explain how the FIR filter is defined in here. So earlier we had the original signal, and and to that original signal we applied FIR filter. So FIR filter, if we are implementing that, we will be applying a set of we will be applying set of delays, or we will be sliding. We will be actually considering different time samples of the signal, and then multiplying this time samples with the filter coefficients. So that can be shown by a block diagram. So I'm going to draw that now. So the signals that are coming in will be stored as values in the system. So the initial time sample that we are taking will be x0, and the second time sample we'll be taking will be x1. Third one will be x2. Sorry, x0, x1, x2, x3, x4. Likewise, we can take time samples, and those time samples will be multiplied with a certain frequency. I mean filter coefficient. If we take the filter coefficient as f0 for the x0 time sample, we can say that, I mean, there are other coefficients that are for the other time samples. So these time samples will be multiplied by certain filter coefficient. So this process will continue for all the different points in this filter. So this filter is created by taking the multiplication with the data samples and the filter coefficients. So the data samples are like this: x0, x1, x2, x3, likewise. So this is the most initial time sample, and this is the second time sample, so third time sample, the fourth one, likewise. So each of these time samples will be stored in a certain memory location in the circuit, or whatever the processing unit. So this Z-1 denotes the delay that is applied on the time sample. So the time samples are delayed using this Z-1 blocks. So whenever you input some data into this stream as the input data, that data will continually be slided into the right using some delays. So in the next time instance, the next set of data will be slided into this process, and the x0 data sample will be removed, and it will be replaced by x1 time sample. So in the second times instance of filtering, or in this process, the time samples that were already initially in this block, in this diagram and in this filtering process, will be replaced by x1. This will be replaced by x1. X1 will be replaced by x2. X3 will replace x2, likewise. So time samples are there, and the time samples will be replacing the initial time samples in these locations. Then finally, once you take the product between the coefficients and the time samples, you will add all those things together. So all these will be added together, and this output will be taken, and that output will be the filtered output. So this will be denoted in time domain as yn equals hn convolution xn. So whatever the process that we have done in here actually corresponds to the convolution process. So this entire block diagram and the process that we have done in here corresponds to the convolution process, but in the time domain. Sorry, Z domain. It had been done in the Z domain. And this will be therefore like turned into time domain, and that will be the convolution based time domain signal. So whatever that is happening inside this process will be considered totally in the Z domain. So this block diagram represents what happens in a like a FIR filter. So FIR filter considers this kind of a process and does this kind of process to compute the filtered output of the signal. So at each time instance, to take a finite sized time samples of a finite size amount. That means like for one time instance, it can take only some set of data samples. So it will take x0, x1, x2, x3, x4, likewise, some finite amount of time samples as the input. And then once it is computed and once it had computed the output for those samples, then the next set of samples will replace these x0, x1, x2, x3, x4 time samples. And likewise, the process will continue until all the time samples are filtered out by this filtering system. So the convolution process is actually done in this process. So basically convolution, which is like a process where you are like multiplying a certain time instance with a delayed version of another function in here, which is the maybe filtering function, multiplying with the delayed version of the input signal, you can obtain the convolution between the filter response and the input signal. So anyway, the convolution operation is done inside this block diagram. So with that, the filtering response is obtained. So for FIR and IIR filters, there are two block diagrams that define their operation. So this is what I have drawn for the FIR filter. For the IIR filter also, we have a certain block diagram that defines its operation. So for the IIR filter, the block diagram is a little bit different, and it is denoted using both input signal and also output signals, delayed versions of the output signals. So before doing that, before drawing that, I will show you the mathematical equation of this FIR filter. So FIR filter's mathematical equation consist of some model like this, which is yn equals k equals naught up to m, mo like some kind of constant tabs. We call this filter tabs. So filter tabs can be finite amount, and in the FIR filter there are only finite amount of filter tabs. So in this filter tabs only, we take the time samples and multiply with the relevant filter coefficients. Then you multiply with the specific filter coefficient. In here, I have taken the filter coefficients as F0, F1, F2, F3 likewise. So if we take in that manner, we can say the filter coefficients will change using Fk likewise. Then the Fk will be multiplied with delayed versions of the input signal. The delayed versions of the input signal can be taken using xn minus k. Right? So delayed versions of the input signal can be taken by xn minus k terms. You multiply with the filter coefficients values. The filter coefficients are something we have to either design or we already know. These are either we already know this, or else we have to like predict it. We have to calculate this filter coefficient values sometimes. So sometimes we know this filter coefficient values. We know the values of the filter coefficients. Sometimes we don't know. So in that case, we have to find them. Then once you know those things, then you can find the output of the filtered signal. So in the FIR filter, the function looks like this, where the FIR filter output is a function of delayed versions of the input signal multiplied with the filter coefficients. And that summation will be done for a finite duration. So this is how it is mentioned. So the FIR filter relies only on the input signals delayed versions, or delayed versions of the input signals samples. So the difference with the FIR filter and the IIR filter is that in the IIR filter, the filter response depends also on the previous output of the filtered signals. So in the IIR filters, the mathematical model that is used to define the IIR filter is that basically it depends on the previous outputs of the filtered signal as well. So if this is the FIR filter, this is for the FIR filter. For the IIR filter, we have another mathematical model, which is given by, let's say in here also the number of taps are number of taps are there. So in here I will be using filter coefficients denoted by B, let's say BK, which are used to multiply with the time samples of the input signal, the delayed versions of the input signal, and then you also add to that the components related to the previous outputs of the filtered signal. In here, it will be taking the minus sign. So in here, you will be taking the summation from k equals 1 up to n, ak, y, n minus k. So this is the delayed versions of the output that we received earlier. So delayed output signals, output samples. So this is the input samples, delayed versions of the input. This is the delayed versions of the output that we have already taken previously. So the IIR filter is therefore a combination of both the input signal components and output signal components. So when we are working with IIR filters, there are more filter coefficients in there to consider, and these filter coefficients will be determined based on the required output. So in the IIR filter, this is the model that is used. IIR filter, this is the model that is used basically. So IIR filter relies on the previous outputs also, not only the inputs to the filter, but also it keeps a storage space to store the values of outputs that we received earlier. So the block diagram of IIR filter will be denoted using that feature. So in here, the block diagram of the FIR filter was determined basically using the input signals time samples of the input signal. We don't need the samples of the output signal in this FIR filter. However, in the IIR filter, we need to consider both the impact from both the input and output time samples. So that we can denote using this diagram. So when we take the IIR filter, we can denote it using this diagram. So the IIR filter I'm drawing in the Z domain using Z blocks. So the input signal will have some components. Each of the components will be multiplied with a certain coefficient. So this is the way of obtaining the time samples of the input. So we can define the coefficients for each time sample. So if you are considering k equals 0, correspond to the xnth time sample, and b0 is the coefficient for xnth time sample. If you are taking in here, you will be obtaining xn minus 1 time sample, and in here you will be having xn minus 2 time sample. Likewise, the time samples will be delayed, and they will be taken into consideration. So this will go on for a finite duration. So after you do the finite duration of delaying, you will be getting the output and multiplying that with the filter coefficient. So each of these will be multiplied with the specific filter coefficient. So once it is done, you will be able to take the summation of all those outputs and then put them all into one location and take the sum of all those values. So these values that you get from this product, you will be able to put into one location and take the sum, and the summation will be then added to another summation, which is the output that you get from the values of the output of the filtered function. So earlier you have got the previous outputs from the filter, and then those outputs will be stored in the computer or the processing unit. So the delayed versions of those outputs will be stored, and those will be multiplied with a certain coefficient. So the multiplication part will be done first. So multiplication with the coefficient will be done. So the coefficient values will be determined in this manner. So the first delayed version of the signal will be multiplied with the coefficient A naught. So in here, if I substitute K equals 1 in here, A1. Yeah, A1 is the first filter coefficient. So so basically you will be in here, you will be multiplying with the A1. Then you will be adding that to the summation in here. Similarly, you are going to take a delayed version, further delayed version of the input output signal yn minus 2, and then take the product with the coefficient A2, then take that as the output. So this process can go on for finite time blocks, finite time delays. This process can go on. So based on the amount of memory storage you have in the computer, you will determine how many storages you are going to do. So at each of these Z minus 1 blocks, you will have some memory of some data. So these data will be stored in the memory. So this data will be stored in the memory, and these data will be stored in the memory. So if we are having 4 blocks of Z minus 1 delays, that means we have 4 memory locations to store these 4 time samples. So since the resources are limited in these computers, you will only have finite number of memory locations. So if you consider this other side also, there will be finite amount of memory locations where you will be storing the data. So this can be FI, it's not a FIR filter, it's a IIR filter. This is a IIR filter. So IIR filter consists of both components of the input signal multiplied with the filter coefficients plus the previous outputs of the filter multiplied with filter coefficients, and the combination of both will result in the output signal of the filter. So this is the output signal of the filter. So output of the filter will be given in here. So it will constitute of all these two combinations, and so like this the FIR filter will compute its output. So that is something regarding the filter response, how the filters will compute the output, right? By taking each of the data points singularly, they will be multiplied with a certain coefficients dedicated to them, and those time samples will be shifted towards the right, and the new time samples will be substituted to the previous locations. So likewise, the field coefficient will like kind of slide the time samples forward and update the time samples with new ones. So likewise, the output will be updated with each new output of the filter. So that operation of IIR filter is like that. So in basically in MATLAB and other simulation tools, you can find a function to take the filtered output of these IIR filters and FIR filters. So you can use those available commands and functions to get the IIR or FIR filter output directly from the simulation platform. So if I like tell you regarding MATLAB, um, MATLAB will produce you the filter output when you give a certain command called filter. There's a command called filter in which you can directly take the filter output. So when you are considering the FIR filter has mainly some limitations, right? FIR filter is a filter which has finite duration output, right? The output will be there for a finite duration only. For the other rest of the time instances, there will not be any output. So the filter response is for a finite duration. Filter response is defined for a finite duration for the FIR filter. So in the FIR filter, sometimes like because of the nature of the FIR filter, the filter might not be able to create a very rigid filter. So in some cases, if I consider the FIR filter implementation, sometimes although if I want to create a very rigid or very rectangular shaped filter, I might not be able to achieve it uh, like in a perfect manner, but I might be able to like create a approximation of the uh, perfect signal that I want to have. If I want to have a low pass filter, the low pass filter will be a function which is approximately equal to the low pass filter, but it is not exactly same or very closely similar to the expected rectangular shape. So in this low pass filter, although I want a rectangular shape, sometimes the curves at the edges will be like not that rectangular. It will be having a small curve, and then therefore that whatever the operation that is happening in the FIR filter will actually be approximating this low pass filter response and not exactly doing or implementing the rigid version of the FIR filter. So sometimes the FIR filter might not be able to do the ideal filter design. So not able to do the ideal filter design. So ideal filter design might not be able to be done using FIR filter. We'll be doing some kind of optimization of the required filter. So it will be doing optimization of the required filter, and it will be therefore a smooth or a filter with maybe some smooth turns and roll off available there. So the approximated version of the original ideal signal will be ideal filter will be implemented in the FIR filter. In the FIR filter, we will be not be able to do the ideal filter design. That's what I'm trying to say. So with that, I think I will just explain to you and show you that in FIR filter, what you can actually, how you can implement the, maybe how you can see the like MATLAB version of the, MATLAB, in MATLAB, how you can see the FIR filter or IIR filter. I will just mention. So this is like MATLAB code. So it's actually not important. I think I will just explain now about the filter function that is available. So in the MATLAB, if you go to help and filter, the filter function that is available in MATLAB is implementing this filter. So this the top equation that is shown in here gives you the filter response. So help filter gives you the way that filter is defined. So filter is defined in this manner. So the filter is giving out an input, giving out this output, and this output is depending on the input signal xn and the output previous outputs that were obtained yn, right? Yn minus 1, yn minus 2, yn minus 3, likewise up to like many time samples of the yn we can obtain. So the combination of the outputs and the inputs are used to find the filter output. In here, can you see like in here we have actually a similar configuration, similar filter related to IIR filter. We have some filter that is similar to IIR filter operation. So in IIR filter operation, we will have both the input and output time samples contribution in the filter output. So this filter that has been implemented in the MATLAB is having both the combination of input signal and output signal components. They have been multiplied with filter coefficients B1, B2, B3 up to about Bn, B plus 1. And then there's coefficients A which relate to the coefficients applied to the output time samples, right? Output time samples of the filtered output. So the coefficients are A1, A2, likewise up to A plus 1. So this is the way that it has been implemented in MATLAB. This is a standard equation that they have used. So using that filter, we can get an output once we define the necessary input data in the command, in the function command. So that's regarding how MATLAB has implemented the filter. So using MATLAB, you can get filter output that is similar to IIR filter once you give the necessary coefficients and input data. So with that, I think I have explained to you about how the filters function. So I will explain to you like some more things related to the filter functions in the upcoming classes. So in today's class, we have gone through these sections basically. So the Fourier transform and its limitations. So the Fourier transform limitations we discussed as not being able to identify sudden changes in the signal in terms of frequency. For example, like Fourier transform is able to give a frequency information about a signal, but it is not able to give like rapid changes in the frequency information. So in such kind of cases, we might have to go for other transform methods such as wavelet transform. The wavelet transform is something that we have to discuss next. So in the second part of our today's session, we had some understanding about the set transform, how we can use a set transform to find parameters of a LTI system. So using that, we can find out statistics about a LTI system. So Z transform is much more simpler than Fourier transform. So therefore, we can move on to using Z transform to do easy calculations, which can also return the same output as Fourier transform. Then FIR and IIR filter overview we have discussed, and we will discuss further regarding FIR and IIR filters in the upcoming sessions. After that, we can also discuss about the wavelet transform. Wavelet transform is used to identify abnormal changes in the signals and identify those sections using something called wavelet. So we will learn about the wavelet and how it can be used in simulations. So with that, I think I will end today's class. So any questions so far? So if you don't have any questions,